or even like different, forgetting the word right now, but different, just different barriers to play that actually come into play and make all these systems talking to each other really difficult. And so that's why rather than having one central computer, we see the shift of like from one to a bunch of different systems that are all interacting with one another and helping with like some smaller tasks, but ultimately all working together to achieve one shared goal, which is to make sure that the flight goes smoothly. So, and as we see over time, we've seen as you might have heard of, with different systems, we see a rise in distributed systems with different technologies that are becoming more and more common nowadays. So whether it is like space travel or even like autonomous cars and being able to talk to each other, like whether it's like self-driving, they need to interact with one another and interact with like some central server so that it can make sure that they don't crash into each other and that things all run smoothly. And so these are both examples of distributed systems where even the most precise components are essential to safety. And even nowadays, we see this with data centers, and now with remote work, and even far before that, we have different data centers, databases all around the world that work in tandem and need to be able to interact and exchange information with one another so that, like, to achieve whatever the shared goal may be. And nowadays, that's where we see it in blockchain. So this is where we see the trust without the trust. The idea of, like I talked about, you want to make sure things run well and run accurately without needing to either trust the people who are behind each individual device or system, so you don't have to trust each individual part, because a lot of the times we see that maybe it's a database server, something that will crash, we need to find workarounds so that we don't have like whole companies or whole databases like servers crashing. So it's essential to make sure that we are able to fight, like kind of tolerate these different changes and barriers to our environment. So we're gonna get into a few definitions now. You might have heard me use, or you might have heard a few of us use some of these earlier on, but these are just some good terms to know. So we're gonna refer to different devices, computers, whatever they may be, as a node. And so nodes are just thought of as like individual, kind of somewhat autonomous entities that can carry out whatever actions are necessary, or like carry out any computer-based actions. And so in between all these nodes, we have communication. And so these message channels are kind of passive information from one node to another. And ultimately, all of them work together to accomplish a shared goal. And this is what the goal, that is the whole point of consensus, is we want to have everyone working together with the same ideas in mind. So this is where we see why consensus is so important. And the biggest challenge, though, so like kind of getting to some of the challenges, we have a lot of different kind of barriers that don't make this super easy. And so the first is that we have all these different devices working autonomously. How are we going to sync them up? Because there is no global clock, and there's nothing that can be a point of reference necessarily to allow all these devices to work well together. And we might have, like I said earlier, we might have certain nodes that drop off the grid, whether it's like Wi-Fi issues, maybe they break, maybe they're hacked, whatever it may be, and maybe we have to make sure that we can work around these things and work without a few nodes not working or not being responsive. So kind of, I guess, the most naive, the most straightforward form of consensus, which we'll get into, is just binary consensus. And so let's just imagine we have a question we're trying to solve, and each computer takes a vote. They'll either vote blue for yes or red for no. And what we'll do, pretty simply, is we'll count up the number of people who voted no, red, and blue for yes. And once whatever has the majority, everyone will agree with that. And so that's just a simple voting mechanism, and that's what we see a lot of the times with maybe votes we've seen here. We can see that in elections. We can see that in so many other different like everyday examples. And so this is where we started off, but we'll see a little later why we need to have and develop more intricate forms of consensus for blockchain. So ultimately, like the big picture here is we want to make sure that, like through consensus, we want to make sure that a bunch of nodes or computers or devices, whatever it may be, can do meaningful work and work together while we have all these other factors that are negatively influencing or providing more and more challenges for this to happen. And so like this is like a little intro, so we'll get into some more of the challenges we see later on. But pretty much like by everything on fire, that just means all the different hurdles that'll be thrown our way. So that's a little intro to consensus right there. Any questions? Okay, sweet. Okay, well, Jade is going to get into the CAP theorem a little bit. Yeah. You get it, Tiger.
Thank you. So in the next section, we're going to be talking about properties of distributed systems and CAP theory. So when building distributed systems, there's a few concerns that we have. And when I'm talking about distributed systems, I'm not just talking about blockchain. More generally, just any distributed system. As we'll see in this section, we'll see a few of the original examples, and then a few other current examples of distributed systems are things like data centers. And if you're familiar with like Google's Hadoop framework for distributed computing. So with distributed computing, there's two main concerns. There's safety concerns, and these are things that cannot happen. So an example is when you're using Google Drive, you're guaranteed that you're not going to lose all your files if all of a sudden the Google front-end server goes down. And the other concern is liveness, and these are things that must happen. And Google Drive must successfully get your file for you every time you click on it. So the correctness of consensus relies upon three things: validity, any value which must be decided upon needs to be proposed by a single node; agreement, which involves all the other non-malicious nodes on the network agreeing on that value; and termination, which is when all the non-faulty nodes eventually decide on the same answer. And the correctness of a distributed system is ambiguous, so it depends on the system. You'll define it for your specific system. That's kind of up to the design of the protocol, but the correctness just needs to imply that all the nodes that are non-malicious and are non-faulty are going to come to the same answer most of the time. So now we're going to begin discussing CAP theorem, and CAP theorem talks about the trade-offs between consistency, availability, and partition tolerance when building distributed systems. It's a fundamental theorem for designing the distributed systems, and we'll see how this applies to crypto blockchains like Bitcoin and Ethereum. So the first aspect of this is consistency. So every node must always provide the most recent state or no state at all. So if, for example, we're all going to get burgers, and every day we all talk to each other about what we want to get for lunch, or what we want to get for lunch, whether we want to get burgers or pizza. We will say we decided pizza yesterday. Everyone on the blockchain, or not on the blockchain, but in this distributed system, should be able to say we got burgers yesterday, or say that we didn't get anything at all, if we're to have a consistent system. Availability is the next concern, and that's the idea that every node always has constant read and write access, so that it's always live on the network and you can always communicate to it. And the last concern is partition tolerance, and that means that the system works despite partitions in the network. And a partition in the network is if some nodes can't reach other nodes on the network. And if we think about the internet and the nodes of mining on Bitcoin and Ethereum, these nodes definitely are not always able to reach each other because the internet does not guarantee that you're connected to every other node. So partition tolerance is the idea of if even a cluster of nodes, say I have 15 nodes in my network and 3 of them over here are completely disconnected from the other 12, we want our system to still be able to come to consensus and reach a decision. So the dilemma is that we can't have an optimal distributed system across all 3 properties, and trade-offs must be made. So it's not that we can't have all 3 of these in a distributed system, because they're all present to some degree on every blockchain, but as we'll see in the following slides, it's impossible to go towards one of the concerns without losing the other one. So if you want to make your system more available, you'll have to sacrifice partition tolerance and consistency, or more of one than the other, because you can't maintain, if you could maintain all of these properties, it'd be a perfect blockchain, and we wouldn't be talking about a lot of the concerns and improvements that have been made to blockchain technology. So in the next sections, we'll do a brief like visual proof of why this is true. This is similar to the more formal academic proof. If we see here, we have, let's treat this red arrow as an input to the system, and we'll treat all the nodes here as currently being blue. So we have two decisions in this system. The system can either, at each time step, vote to be red or vote to be blue. So at the first time step, we have all of our 4 nodes in the system. They're all connected, and we see that they are all in agreement. If we go back to this slide, we'll see the consistency slide. Every node is always at the most recent state. So here we see all the nodes are blue, and we have a red input. Once the red input comes in, they all change, and we see that the they maintain the consensus, and also the input is instant, so we maintain the availability. Now we also will add an output arrow, and we'll show partition tolerance. So if we were to draw a line that disconnects 1 and 2 and 3 and 4, all of a sudden inputs we won't be able to maintain availability and consistency at the same time. So in this example, if it's both consistent and available, we know that it can't be partition tolerant, because if 1 and 3, if we see here 1 and 3 are their own group and 2 and 4 have become their own group, so if an input comes in now that says blue to node 1, it'll communicate it to node 3, so node 1 and node 3 will be of the understanding that we're voting for blue, but node 2 and 4 will not have gotten the memo, so then we have 2 votes for each, and consensus can't be reached. On the left, we see the example I was talking about. On the left, we see a different example. If it is partition tolerant and available at the same time, it won't be consistent, because when we feed in the red input, it won't go to blue, as we were discussing earlier. And if it's both partition tolerant and consistent, it won't be available, because if we want to maintain the fact that we can draw a line between 1 and 3 and 2 and 4, and we'll all still know what the proper last decision was, that we all decided on red or blue in the previous time step, then we can't allow for new inputs to be fed into the network constantly. So a few notes on this. Partition tolerance is a given for pretty much any system, especially all of these distributed systems and the blockchain. The trade-off is between C and A in reality, because for the blockchain, partition tolerance is a must, because as I was mentioning earlier, it's basically a guarantee. We cannot guarantee at any time, because of how the internet works, that every node on the network will be able to reach every other network on every other node on Earth. There's always internet shortages and downtime. So we have to be able to, even if we can't talk to all the networks, all the nodes on the network, reach a decision. So the only things that we will be able to really trade between are consistency and availability. And another side note is just CAP's theorem is a good way to think about the design of a distributed system and why certain choices need to be made, but it's often taken too far. And if the fact that it's not that you can't have consistency or you can't have availability if you have partition tolerance in the other one, it's that you can't optimally in the middle get all 3 perfectly. You have to make trade-offs. Any questions? Okay, let me go back and try to explain it a little more. Is there something specific about it that was confusing?
No, I don't fully get it.
Sounds good. So the idea of partition tolerance is that our system needs to be able to reach a decision whether or not all the nodes on the network are live. So with Bitcoin, for example, I don't know the exact number, but let's say there's thousands and thousands of miners around the world. It's almost a guarantee that at any point, someone's power is going to go out, someone's computer is going to crash and malfunction, the internet will go out in one area and we won't be able to connect to that node. There's not an internet connection to a node running in a certain area, or it needs to go through so many connections that the latency is really high. So we need to, in this scenario, still be able to come to a decision. Does that part of the partition tolerance make sense? Okay. And then here we see like that partition is the disconnection in the network. And when you have that partition, because the network's no longer like immediately connected, so a decision, if you think about it like neurons firing, when a neuron fires, the decision goes very quickly through all of them. But if you all of a sudden have a partition, it's not going to be able to go very quickly through. So you'll either have to decide that, okay, just half the network will know, and the other half will have a different idea. And that's the case where we've maintained availability, but we've sacrificed the agreement. And the other case is we say that the whole network will still be in agreement, but we'll just not allow new inputs so we don't get confused. Does that make sense? Awesome. Any more questions on this section?
So this line in the middle kind of symbolizes that some of it will always be offline.
Yeah, the line in the middle symbolizes that these nodes cannot reach each other. It doesn't need to be understood only in the context of like the internet being out, because in other distributed systems there's other reasons. But yeah, that is in blockchains what's often the reason, and the reason we need partition tolerance. Any more questions on this section?
Like, do you have an example of another distributed system where this line is something else?
Yeah, so another distributed system that involves a lot of these concepts is a data center. So things like AWS and Google Cloud store large volumes of data in these data centers, and it's not just one single computer, it's racks and racks of servers. So they're not just storing the same information on every server, so they need to find a way to spread the information across all the servers while not being able to rely upon the individual uptime of any one server, because when you have hundreds of servers running in a data center all day, there's like this certain probability, it's like a guarantee that certain servers will fry every day. So there's certain probability that servers fry every day. So they go ahead and they calculate how many servers on average will be down, and they have like a really good idea of that. And then they decide an amount of redundancy they need to add into the system to, with even that downtime, still be able to at an acceptable rate. Does that example make sense?
Is there a time tolerance built in for all this? Like, if the servers are down for X amount of time, does that have any bearing on?
That's a good question. So one thing to note is that the idea of partition tolerance is that the network will keep moving on without them. So even if they're down permanently, the idea is that the network is so big and distributed that it doesn't need any of these individual actors to keep functioning. So if a few individuals are malicious, or if they get off the network will continue to function without them. So it just considers them out. So like the idea behind consensus mechanisms is a way to come to a decision without trusting one central person. So there's bound to be people in the system that are acting maliciously and are not following the rules. So the same idea that applies to we can't have malicious actors affecting it applies to if people are offline, they're also just like not part of the network, and the network is built in a way that it can move on without them. Any last questions? Awesome, thank you. Now Nate will talk about voting-based consensus.
How are we doing, everybody? Yeah? Woo! I know, it's middle of midterm season, so I know everyone's probably going through the works right now, but thank you all for coming to lecture, whether in person or virtual. Okay, so let's get into it. Well, you know what, take on a nice tour. Imagine we're on a quick vacation. So pretty much I'm just going to show you a few photos to set the scene for our next group of slides here, our next mechanism. But these are a group of islands in the, I believe it is the Ionian area of Greece. And these are called the islands of Paxos. And the reason why these are important is because these are actually the basis, in addition to just being a Greek island, but they are the basis of a consensus algorithm that is really widely used. So we'll just get right into it here. So back in the day, so Paxos had a parliament, and the way they actually conduct their government was as follows. So they'd have three distinct roles. The first was the proposer, and this was a legislator who would advocate like the requests of a citizen or multiple citizens, and then work towards actually implementing this in their government one way or another. The acceptor is also a legislator, but these acceptors are voters, and so these are the people who actually vote on different decrees or different things that are hopefully going to be passed within the government and within the society. And then the learner is someone who is the record keeper. And so the learner remembers and carries out the results for the citizens. And one other component that I'll just get into before we explain the rest is the idea of quorum. And so a quorum is quite simply just a majority. And any two quorums must overlap. So this will make more sense a little bit about the quorum overlap. But you can just think of quorum as a majority. So the process is as follows. So the citizens talk to the proposer, and they go to the proposer and say, well, hey, I have something that I want to propose. I have, let's just say, like whatever it may be, they have some rule or some change that they'd like to see within their community. And so within the Paxos Parliament, the proposer, acceptor, and learner discuss. And so each decree, first off, has a number and value. So there's some kind of numeric and like kind of alphanumeric value associated with every decree that's passed. And like pretty much if quorum is achieved, so if the majority or if there is consensus, then the decree passes. And from there, the learner passes on this information to the citizens and tells them that the decree passes. So this is just kind of an analogy that was at times actually the basis and some inspiration for what we see in the Paxos algorithm, which is also a form of consensus. So we see that we can draw a few parallels here. So the legislators in the system are the servers, and we have a server in the situation. At the same time, we might have what we see as the citizens in the Paxonian parliament would be the same as a client program. So something that needs to be run or somehow executed to actually work. And then finally, the current law is the state of the database. So whether there's something that is pending, maybe something is passed, and is being pushed to all other databases or servers, those are different ways that we can think about kind of the idea of like law or like what the current state is here. So what we see is that this is actually the basis for a lot of different mechanisms and algorithms that we use, that like we see in day-to-day life. And so the reason why these are so effective is because like Paxos is the home of a family. It's kind of like an overarching, like an umbrella term for a bunch of different types of consensus, consensus algorithms. And so we have different ones that are more niche to target different use cases or different needs. So a few of the benefits are that one, it has great performance. So it is pretty efficient, and because of this, we can see that it is used to replicate large sets of data. So it is used in a lot of larger scale operations. So that's why here, like these are just some of the groups that have used it in the past. So that being said, while it is pretty effective, it can be pretty complicated. And so over time, we saw the development of Raft, which is another consensus mechanism, but it is designed to be a much easier alternative to Paxos. And actually, if you look at this photo here, the reason why it is a raft and partially why, like, kind of the idea behind the name Raft was that you're like, escaping one of the Paxonian islands because they are too complicated. So it really is seen as an escape and an alternate to Paxos. And so what we see is it takes like more of a leader-based approach, which I'll get into in a minute. And the leader is responsible for managing all these different transaction logs that are on servers and kind of distributing this information so that everyone has the same record of information. So yeah, and then if anyone's heard of JP Morgan's Quorum, this is also they use Raft-Based Consensus. So this is something you could dive into and check out later on if you're still interested. So the way Raft works is follows. So a Raft cluster, just a group of nodes or devices, people, whatever it may be, has one and only one elected leader. And so this leader takes on a few roles. So they communicate directly with the client, and they run. And so what this means is they kind of help to facilitate different actions that are being given to them. So like we saw with different transactions, like maybe we have like in Bitcoin, we have things that are posed in the mempool, and then whoever proposes the next block or whoever solves that, is like able to solve the hashing algorithm first, will be able to select which different transactions they want to include in the next block that they propose. In the same way, this the leader is the one who's facilitating some of these transactions and making sure things run smoothly. But most importantly, they make sure that all this is logged really clearly. And so this leader will lead until a few things happen. So the leader is permanently leader until either it fails, so if they mess up somehow, if they make a mistake, act maliciously, and the other way is if they disconnect. So if they're no longer connected and people can't really communicate with the leader anymore. And so the way we have this communication is as follows here. So a leader sends out little heartbeats, which you can think of just like little pings or confirmations that the leader is still active and like up and running on the network. And if other nodes no longer receive these heartbeats or these pings, then they start an election cycle, which is a random internal timer. And the first one whose timer runs, completes or times out, will be the new leader. So pretty much everyone is kind of on call and waiting for the leader to no longer send out these heartbeats. And once we don't see any more heartbeats, then they'll start their timers, and the first one whose timer times out will be the new leader. And just to get into a little more about the idea of the log replication, the way this works is that the leader accepts all the client requests. So the leader is the one that is managing these different requests. And at the same time, the leader also keeps track of other nodes and makes sure that all other nodes have followed that request. So the leader is keeping track of itself, the requests, and all the other nodes to make sure that everything is done in unison. Okay, any questions there? Yeah. JP Morgan Quorum. It's just, I guess if you want to, you could talk about it a little more.
Tried to establish blockchain technology at JP Morgan. They've since sold it to Consensus. You know what Consensus is? When they stopped believing in blockchain like a year ago. And then now they're back on blockchain. So now they're building a new thing.
Well,
Quorum is not JP Morgan. I don't know what they're
Yeah.
doing for these days.
Well, if you remember, back in lecture 2, what was your favorite slide was the JP Morgan slide. If you want to check that out later, it talks a little bit about the progression of JP Morgan's blockchain use and ideologies. Yeah, the graph, exactly. Like the price of Bitcoin at the same time with all the different remarks about what? Yeah, they dumped it, and I think they're. Depends on who you ask. It's not too difficult, but sometimes it's difficult to implement, like even within banks, because they have these systems that they've been using for so many decades that it's not always as easy to make such drastic changes with blockchain. Yeah. Any other questions? Okay. So now we'll get into Byzantine fault tolerance. So this all goes back to an age-old question, which was the Byzantine generals problem. And this was something that actually referred to a real kind of like military setup, and I'll get into that in a second, but pretty much the Byzantine generals problem poses a situation where we have a commander, like a commander-in-chief, and then 2 generals, and we want to make sure that because all these different, like the commander and the 2 generals are at different locations, we want to find a way that these 3 people can communicate effectively and clearly. So the way that we do this is, so I'll kind of pose the question here, but here's the context of the problem. So a general and their lieutenants are planning to attack a city, and they're waiting for the general to give the orders to either attack or retreat, but they can't trust anyone. So neither the general nor each other. So the general must issue an order, and the lieutenants will share the order amongst each other in order to reach an honest consensus. So the way this works, the lieutenant gives an order, and then they will communicate among each other, or among themselves. So our consensus, and this is the way we check if the problem is solved, we know our consensus is correct if all loyal lieutenants obey the same order, so everyone's on the same page, and if the general is loyal, all loyal lieutenants obey the orders sent to them by the general. So we see that it's the same order, and assuming that the general is loyal, everyone does the same thing. So this is how we ensure that everyone's on the same page and everyone's doing the right thing in the situation. So one of the challenges here, and this is where we see kind of the idea of like Byzantine faults, and like we talked a little bit about, I mean, JJ talked about fault tolerance a little bit, but we have these external factors that get in the way and make communication a little difficult. And so we're going to imagine in every scenario here that we have one malicious node here. I guess we can think of it as a node or like one malicious member in this situation. So in the first scenario, we see that we get, actually in both scenarios, we get conflicting messages in both of the orders depending on who is giving false orders. And so I'll explain the first one here. So the first example here, if the commander tells both to attack and lieutenant is like malicious in some way, then the lieutenant will change the order and tell Lieutenant 2 will tell Lieutenant 1 to retreat. And we see Lieutenant 1 is getting conflicting orders in this scenario. And then if we see that the commander or the general is actually the malicious one here, the commander might tell 1 to attack and 1 to retreat, and Lieutenant 2 is just passing on what Lieutenant hears. And at the same time, we're still getting the same order, and we're still getting conflicting orders. So what this goes to show is regardless of whoever is malicious, out of commander or Lieutenant 2, the Lieutenant 1 is getting the same orders, and there's no way to distinguish which one is the malicious one. So what this means is that in terms of this Byzantine general problem, we don't get a solution for any amount of traders that is over a third. So we have to assume that in these Byzantine examples that less than 1/3 of the nodes or of the generals, however many, like the commanders, lieutenants, however many people or devices or nodes are involved, we have to assume that less than 1/3 are malicious or tampered with or unresponsive, whatever it may be, or else this won't work. And we won't be able to create consensus, and we won't have a sense of truth and accuracy here. So just kind of drawing the connection here, we see that the generals here are different nodes, like I mentioned. So different devices that communicate with one another and share information, share orders. And the trader general is either a faulty or malicious node, which we'll call a Byzantine node. And the geographic distance here, where in the general problem we have, like in the general's problem, we have different stations all around the world, whatever it may be. We have a distributed network of devices. And so that's what we see in the blockchain. And then the ideas of whether to attack or retreat, we can translate over and make it and see the analogy of that being related to the idea of like a transaction log or consensus on history. So tracking exactly what happened, what interactions happened on the blockchain. So any questions about the Byzantine generals problem? Yeah.
What changes when you have less than 1/3?
So we'll see that in a second, but pretty much the more devices you have, you're able to actually have, push through these and, if we even go back, I'm not gonna go all the way back to the beginning, but we saw if we have, let's say 10 devices and one of them is faulty, we have different workarounds. And so we'll see these, in a second, some different examples of ways that we can work around this 1/3 limitation and allow for more consensus to happen where you can have more than 1/3 of faulty nodes. Anything else?
Faulty and malicious nodes and all that, is that something that happens often, like in the real world applications?
Yeah, so we can think of them as, a lot of times it's people, it can either be, I guess the way that we've been talking about it earlier is referred to people who are trying to tamper with the network. Maybe they're trying to, at least in a Bitcoin context, they're trying to game the system so that they can make more money. But a lot of times what we see in, I guess, cryptocurrency examples is devices that go offline, servers that are shut down, Wi-Fi, kind of different barriers to having these nodes be fully interactive in the network. So anything that might inhibit a device from connecting and being fully involved. Does that help at all? Yeah. Okay. Anything else? Okay, well, we'll go on to some of the consensus mechanisms that are used in pretty much most of what I'm guessing you've all heard about. So we will get into some Nocomoto Consensus. So just to make kind of a generalization here, so thinking about what we talked about in the past with the Byzantine with the Byzantine general problem, we have some kind of election. So a leader is elected through some sort of lottery process, whatever it is. Whether we saw in Raft, whether it's if the leader goes offline, then there's a random timer, and when it times out, then that's the new leader. But there is some kind of lottery process here, and then from there, the leader creates the next block, and then others vote implicitly by including the block in their chain. And what that means is if they continue and decide to mine on it, and if they actually continue to go forward with the next set of transactions that the new leader has proposed, then they are implicitly including it and choosing to accept the block. So the real challenge with this is figuring out this whole lottery system, because with so many distributed devices, it's really difficult to find a way to randomly elect a leader that is fair and kind of upholds the safety of the network, because this is what we need for things to run effectively. So this is actually a question for everyone. So everyone's heard of proof of work. Hopefully a lot of you have heard about proof of work, but does anyone just kind of popcorn out some things? What are some of the resources that can be spent in consensus? And so I'll give an example. So we use proof of work as a way to, because that factors into at least in Bitcoin, to the, well, you know what? I'll just go on, and then I feel like I didn't really pose that question well, so we'll just go on to this, and then we can pause for questions in a second. But the whole idea is that we need to use some kind of resource and spend it so that we can actually be a part of the progression of the network. And so what that means is, to be elected for this lottery system, you need to kind of put some kind of resource into it so that you can throw your name in the hat, or throw your hat in the ring, and kind of make yourself viable for the election process. So something that we've seen so far, we've seen electricity and energy being used. And this is the idea of proof of work. So by putting in computational power, you're able to try to solve this hashing function, or you're trying to solve solve for the nonce and find your value that fits within the boundaries specified by the nonce, all those things that we talked about a few lectures ago. But there are other things that we can actually use. And as we see, Bitcoin takes up a lot of energy. And that's why we've heard a lot about the environmental factors that come from blockchain, and why people are actually starting to phase it out a little bit is because Bitcoin is using so much energy, and that energy doesn't necessarily go towards anything other than electing that next leader, so to speak. So we can see that currency is something that can be used. So people can put up currency, and this is what we're kind of seeing in DeFi a little bit with the idea of collateral. And if it doesn't make any sense, then we'll get into it later, so don't worry about it. But you can give some currency, you can give some money of some sort as a way to show your worth and show how much you want to be involved in the network. And maybe the more money you put in, that'll directly transfer over to how likely you are to be the next leader and propose the next block. Something else we can do too, like we saw in Raft, was time. With this random timer, that's something you can prove. And that's a resource that can be spent and can be randomized so that you kind of elect the next leader. Something also even too is storage space, whether it's on your local device, on some kind of cloud. You can put up storage space, and even reputation. You can track your past history on a certain blockchain, and from that can be a way to prove your worth and show your dedication to the network. So we've talked about proof of work a little bit, but now we're going to get into something called proof of stake. And some of you might have heard that Ethereum is making the shift, or likely making the shift, to proof of stake. And what this means is, rather than using energy and electricity as the resource that's being used, we see that the native blockchain's currency, or some kind of currency, is what's being used. And so the way this works is, at a certain point when they want to be involved, the people, so a little terminology here. So the validators in proof of stake are called miners. And what they do is they'll lock up stakes. So once they want to be involved, they'll provide some amount of money, some amount of native ETH, assuming we're talking about Ethereum here. They will put some ETH, and it'll be locked up. And from there, once they have a certain amount of money that is inaccessible for them, and it is involved in the network, then they will be able to start to interact and work with consensus. And this will allow them to potentially be the next ones who, be like the next leader, so to speak. And so there are a few different, they're kind of like two different flavors of proof of stake, but this is kind of the way that it works. Pretty generally, we'll see more on this kind of this right side, because that provides a lot more security. But I'll just talk this a little bit. So for starters, so we have a randomly chosen validator based on the proportional stake invested. So people who provide more stake, who put in more ETH, or put in more tokens to the, and then lock it up, and kind of pretty much you can think of it as just like giving it to the network and putting it away so they can't access it, and doing that will show your loyalty to the network. From there, then maybe the more you put in, so we either have a situation where the chosen validator creates a block and everyone agrees with it. Because you've already proven yourself to the network, you put in the stake, these local currencies, or like the native currency, then no one has any reason not to trust you. But if you want a more safe approach, we'll see that the chosen validator proposes a new block and everyone has to vote on it. And what this does too is it provides an extra layer of security and makes sure that everything that is run is pretty much okayed by the majority of the network. And then finally, after these 2 points, we'll see that the chosen validator gets the block reward and the transaction fees, just like we talked about last time. So we've talked about stake, which provides talks about local currencies, and we've talked about work, like proof of work, which is energy, electricity. We also have proof of space, which is another way to use either disk space or some other kind of storage, and by consuming space and actually using that as the economic resource that is scarce, that is also a way to prove the loyalty to the network. And so, I mean, I guess even to me, it sounds a little strange, but it is something that works because there is a finite amount of storage space that can be given and used in any given scenario. And because of this provides some kind of loyalty and scarcity because space does have a cost associated with it. Something else too, which is similar to Raft, but it's the idea of proof of elapsed time. And so rather than actually spending your mining power and using electricity, you spend time. And so you might use like a trusted execution environment. Then what you'll do is you'll ask it to wait a random amount of time, and then it's a way to to verify that you have waited this amount of time. And so while it does seem also a little strange to use as a consensus mechanism, it works because it consumes time in a random quantity. Or everyone consumes time, and because everyone has like a random amount of time that they need to wait, it provides some kind of random component, and time is like an economically scarce resource. So it's not something that can be like artificially replicated or adjusted. So it allows for kind of a random way to consume some resource and then use it to elect the next leader. Okay. Any questions there? Yeah, good. Yeah. What was that? So in proof of stake, it's just locked up, and so as long as you will, for all the time that you will be a miner, it's gonna be inaccessible to you. So you temporarily don't have any access to it. I mean, you can think about it like maybe if you take out a loan from a bank, they might take your mortgage or something as a form of collateral, like something that they hold on to or they have control over until you fully pay back the loan. That's similar to proof of stake. It's like while you are a miner in the network, you're not going to have access to these funds, but you should be able to get them when you are all done. But that actually brings up, there is another consensus mechanism, or like a proof, which is proof of burn. And then what you do is the way you prove your loyalty to the network is you take some tokens and you send them to to an address that doesn't have anyone attached to it. So what you're essentially doing is just throwing away money as a way to prove your dedication to the network. And it's definitely one of the more edgier ways to do it because no one gets that money and it kind of is a waste of money, but it is a way to prove an economically scarce resource and use that in a voting process or in an election process. Any other questions? Am I going too fast? I mean, how's it? Am I going too fast? Okay. Well, I'll slow down a little bit. Yeah, let's start in the front and go back. Yeah. So there are a lot of different. Well, with each new resource that's being used, it takes a lot of regulation or not necessarily regulation, but understanding how they work in comparison to other ones. And so at least with space, I mean, you kind of have to understand the ideas of like, well, how can you maybe use databases? How can you use just like normal computer storage, whatever it might be, RAM, to contribute them? And so like kind of contribute to like the overall idea of storage. And so even for a lot of these, a lot of them, like they are being used, but the reason they're less common is because a lot of the kind of other tangential components aren't fully explored. And so there's a lot more to explore, and like there are a lot more workarounds. And so because they're not really necessarily being used quite as much because they're like kind of there's more leeway and there are like more loopholes pretty much, if that makes any sense. So they're like less explored. Actually, do either of you have any thoughts on that? Jay, did you have any thoughts on why we're pretty much just using proof of work, proof of stake, and we don't really use proof of elapsed time and storage quite as much?
So proof of work is like the first consensus mechanism that was feasible to run distributed systems like this. So when like Satoshi Nakamoto released it, it was the first time something like this had been implemented in a way where it could actually be used in practice. With proof of stake, as we'll see later in the lecture, a lot of blockchains are moving towards that really quickly. But proof of elapsed time actually isn't, it's like an idea. The idea is that you could use time as a way to prove your work, but it's not been implemented in a full way where it could support a blockchain. And you're talking about proof of storage? Yeah, proof of storage doesn't really make as much sense for something like a cryptocurrency blockchain, but for something like a file storage blockchain, it's used commonly.
So I guess, yeah, JJ brings up a good point, which is that it really depends on the type of blockchain that's being used. And so like we've heard of Filecoin, which uses, which actually is used typically in conjunction with like file storage and different file management. So it depends on, like the reason I think, the way I think about it, we hear a lot more about cryptocurrencies, and because of that, the ones that make the most sense to use are either proof of work or proof of stake. Okay, does that answer your question? Yeah. Okay, great. Yeah. It's all profit. It's all to make money. It's all to make transaction fees and to get the rewards that are gained from actually allowing for these things to execute. Yeah. 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 Wait, sorry, can you repeat that one more time? If in proof of stake, if sorry, what was that last? That a leader can what? Oh, that's only putting legit information. And so this is where we come back to this voting process. So a lot of the times, that's why we see a big discrepancy in safety. So like there's a big shift because if the like the leader, the validator, just if we have a situation on the left, then whatever they put, we don't necessarily trust it beyond the fact that they have deposited this amount of stake and they like put their tokens into the and like locked them up. And the kind of the implication here is that if they do something that is clearly wrong or malicious, then they'll lose this stake. And so that's the first. That's kind of how we assure that. That's how we make sure that everyone will act honestly. And that's why a lot of times we also need this added layer of voting. Any other questions? Yeah. Was proof of time the same as proof of what? History. Oh, of history? I'm not entirely sure. I think time refers to like this kind of random time generator, or kind of like a random internal timer. I'm not exactly sure about history, but I will look that up and I'll get back to you on that. Hey. Anything else? Okay, by a show of thumbs, if you want me to speed up, thumbs up, go at the same pace, thumbs sideways, and then slow down, thumbs down. Okay. Okay, so right around the same, maybe a little bit slower. Sweet, thanks everyone. Okay, so one of our last sections is on federated consensus. And pretty much, so this is where we're starting to think bigger picture. And a lot of the time, some of the challenges are that, well, if we have, I mean, we've looked at examples with 3 different nodes. If we want to have a situation where we scale this and have a lot more devices or nodes that are involved, how are we going to make sure that we can get consensus among everyone? So in a distributed system, a quorum is a set of nodes that is sufficient to reach agreement. So similar to what we talked about earlier in the Byzantine general problem. So this is the issue. Well, so what if we don't actually trust all the nodes in the network? Because if we have hundreds of thousands of nodes, we can have these giant networks that make it virtually impossible to trust everyone and interact with everyone in the same way. So what we see is we're able to solve this by creating smaller subgroups. And these are what we call quorum slices. And what quorum slices are just like smaller subsets of the overall network that kind of band together and trust each other. And so this is just a little example right here. So imagine we have this purple node right here. This purple node is, the question they're posed is, what color is the crayon? They're all trying to answer it and come to a consensus. So the purple node thinks that the crayon is red. But the blue node thinks that it's actually green. And so right now we have some disagreement and we have not come to consensus yet. So then because we see this quorum slice and everyone in this group has agreed, we can convince this one purple node that the crayon is actually green. And so it's kind of the idea kind of relies on strength in numbers. Once people come to consensus, and the more people that are in agreement about something, they can convince the smaller outliers to join them and create overall consensus for every node. So this is where it comes down to a different idea where each individual node decides on other participants that they trust, and after these smaller like kind of trust links have been built, we see more and more trust that comes from that comes from these like quorum slices. And so you can think about it like this also. If you imagine these 3 nodes, so the red, blue, and yellow nodes kind of as one node now. Because they're all in agreement, they pretty much serve as one node. Because they'll trust each other and they're going to act in the same way and make the same decision, then it pretty much distills the number of nodes down from a lot to a little. So now we have consensus. So now you might be asking, well, what happens if we have more than one set of nodes that are like forming a quorum slice? So and this is where we get a quorum intersection. And so this idea is quorum slices that come together will slowly convince other quorum slices and form like this larger quorum. And so just like I talked about, it'll create more and more agreement among the nodes. And so we have actually 2 different outcomes for this. So we either get all the quorums to agree, and so like we see here, we have a quorum slice up top, the purple quorum slice, and then the blue one. And because there is this overlap, we can now essentially through the red, white, and yellow nodes, we can create a quorum, like a larger quorum slice with the purple and blue nodes. And if there are 2 quorum slices that don't come to agreement and don't actually agree, then we get disjoint quorums, and they agree on different things. And so this brings up another challenge, but I won't get into that right now, but it just shows that we don't always necessarily have full agreement. But federated Byzantine agreement can help us to kind of take a lot of different nodes and distill them down into larger groups of consensus. So quite simply, I'll just go through a quick example here. So everyone's trying to decide where they want to go for lunch. This is kind of going back to the problem we saw at the beginning. They all want to decide on lunch. So right now, let's say Brian wants pizza, but then the other 2 want burgers because they're cheap burgers. So because of this, now Brian has agreed because of Omkar and because of these other 2 nodes. So pretty much what we see here is these other 2 nodes on the right were able to convince the node on the left that pizza or that burgers was the way to go. But when we bring more and more nodes into the equation, we have someone else that wants to join. And so we're able to, like, as we increase the number of nodes, we're able to form these quorum slices and have these other subsets that that are all dependent on trust. And so like we see here, the node on the far left only trusts the two nodes on the far left right there, like the two middle left nodes. And because of this, we're seeing trust being just kind of demonstrated through quorum slices. And so these are just kind of, and I guess quorum slices are a little more abstract than I've made them out to be. You can just think of people who are on the same page and who trust each other. You can just assume that they will act in the same way and they trust each other, so you can think of them all as like one bigger group. So right here, as we see, we have two different quorum slices, and we're able to get consensus because we have an overlap between everyone. And so as long as you have at least one node that is kind of like a middle ground between two parties, then we can create consensus among everyone. So a few of the benefits of this, and kind of thinking about more practical applications, a few of the benefits are that, one, we have decentralized control. So there is no one central authority that is authorizing all this consensus. And this is where we're seeing, like going back to the trust without trust, you don't need to trust everyone by any means. You can trust a select amount of people, and we can still come to a consensus, and things will still execute and operate in the same way as having one central party involved. Next, so we have low latency, so things are done really quickly. Consensus can be achieved through quorum slices really quickly, and through overlapping consensus, we see that we are able to get somewhat similar results as we are to one central party. So it doesn't really take that long for everyone to come to an agreement. And that's important for transactions and for just kind of overall blockchain as a whole, if things need to be efficient or else people will be hesitant to adopt them. And finally, there is flexible trust like we saw. So nodes choose who they trust, and they don't have to trust the entire network. So any questions about that section? Yeah, okay. Does everyone trust someone in this room? I can kind of tell by who you're sitting next to. Yeah? That's good, because if everyone trusts each other, then we can all come to consensus. Okay. So I think we have one more section. What? Oh yeah, I'll reload it. We have one more section, which I'm going to reload so that. Yeah, we'll take a quick 3-minute break, and then we just have one more quick bonus section from JJ, which talks about kind of more of the future of consensus mechanisms. Okay. Okay, well, I'll call you all back at 7:20. Take this last section. Oh, that's the funniest thing actually. What time do you go to bed? 1? What time do you wake up? 9, 8?
We left at 6:30 and then I went back to bed. So 9.
We had a full-on conversation, spread out every 2 hours.
That was so funny.
I know.
JJ.
No, he's fucking smart. He texted at 1.
good? Yeah, can you represent?
I'd like the screen. You can do whatever you want.
It's good.
Why is this?
Okay, I think we're gonna call the break to an end and get started here. Excuse me? I think we're gonna get back to starting the class here. Okay, thank you guys all for being here. Hey, excuse me? All right. Thank you guys all for being here. It's nice to have everyone's face and appreciate you guys hanging in this whole time with us. This is a new section to this lecture, so at the end, if you guys are confused about anything, please feel free to ask me questions. I'm sure there's stuff that's missing or not super clear, so would really appreciate any feedback. We're going to talk about the future of consensus mechanisms, and that's mainly proof of stake. So Ethereum's going to be transitioning to proof of stake soon. Ethereum's been running on proof of work since its inception, just like Bitcoin. And proof of work, as Nate mentioned earlier, and we've mentioned throughout this course, requires a ton of computational power to be expended on basically a useless task. The only point of the computation is to have that scarce resource that he was talking about in Nocomoto Consensus. So it consumes a lot of energy that could be avoided. It's estimated that Ethereum and Bitcoin combined will consume this year more power than individually Ukraine and Egypt. In December 2020, the proof of stake chain Beacon Chain was launched in parallel to Ethereum mainnet by the Ethereum Foundation. There's going to be a merge where Ethereum mainnet is merged onto proof of stake and is no longer proof of work. Right now, they're both in parallel, but in either Q1 or Q2 of 2022, they estimate to have the merge. It'll dramatically decrease the power usage. Some figures suggest up to 99.5% lower. And it'll also make the blockchain closer to the vision of decentralization, because if you increase the number of nodes, which this should do, it's more the idea of a truly decentralized system where anyone in this class could pick up their laptop or their phone and hop on and become a validator. But currently, with things like proof of work, the barrier of entry is really high because you need to spend a lot of money on ASICs and power and land, and most of the hash power on the Bitcoin network is concentrated in certain places on Earth in like giant data centers. So the merge, how will the actual Ethereum merge from proof of work to proof of stake happen? Details about the implementation are still in development, but the idea is that ETH 2.0 will have 64 different blockchains in it. They'll be called shard chains, and they may or may not be able to execute smart contracts. They may just store data. That's something that the Ethereum Foundation is still discussing. This will increase the scalability of the Ethereum network dramatically. It will also allow smaller amounts of data for each individual node to have to deal with. They won't be dealing with all of the network's transactions. They'll be dealing with a subset of 1/64th of them. And as more and more transactions and more dApps are built on Ethereum, and if it is to truly be adopted as a wide technology, that's something that will have to happen. Mainnet when mainnet is finally ported over, it'll be ported over as just a new shard, and it's not guaranteed yet whether the other shards will be up before or after that. Avalanche, now we'll talk about, is another consensus protocol that's become really popular in recent years and has a lot of backing by blockchain developers. So Ava Labs is a company founded by Cornell Associate Professor Emin Gun. I'm sorry, I butchered his name, but there's his name if you want to look him up. As of today, it's the number 14 coin on coin market cap and has 13 billion plus market cap and 900 million plus volume per day. The platform was launched in fall 2020, and many popular projects that are on Ethereum or other blockchains have also launched on Avalanche. USDT and SushiSwap are examples of this. The consensus mechanism is a combination of proof of stake and Avalanche consensus, which we'll explain shortly. And adoption by developers has been pretty strong so far because Avalanche is Ethereum virtual machine compatible, or EVM compatible, which means that smart contracts on Ethereum can be easily ported over, and with Avalanche's Ethereum bridge, so can ERC20 tokens. So if you have an ERC20 token like Ethereum or USDC on Ethereum, because of the way they've built this compatibility, you can send it over to the Avalanche blockchain and have it exist there. And what EVM is basically, if you're familiar with the idea of virtual machines, it's like a digital computer that allows us to run our code on a system where we're going to be able to guarantee the requirements, because we're not depending on the hardware we have here, we're depending on the virtual hardware that it's going to execute through. So EVM allows the smart contracts that you write in Solidity for Ethereum to just be ported over to Avalanche, because their compilers will compile it down to Avalanche for you. Avalanche Consensus is proof of stake with a modification of the core data structure used to store transactions in the blockchain. We have that linked list with all the Merkle trees of transactions, and instead of using blocks of transactions here, we use a DAG with a few modified properties. In Bitcoin, time to finality for transactions is 1 hour. We've discussed this in a few previous weeks when we were discussing all of the other attack vectors on the Bitcoin network. We talked about how you have to wait an hour to see if those transactions are actually going to be included and to pay out the rewards, because it could be the case where the miner's not going to get the rewards in a few blocks. But with Avalanche, also with Ethereum, the time is around 1 minute, which is a lot better, and there's a new block every 14 seconds. And this could improve with ETH 2.0 and is expected to improve. But it's still not the same sort of finality as Avalanche. Avalanche has time to finality in the range of like 2 to 3 seconds, and you don't even have to wait a minute for multiple confirmations on the chain because it's not structured in the same way. The energy usage is dramatically reduced. There's no wasted computation, and it's way more scalable than Bitcoin or Ethereum as it is in its current iteration on proof of work. So now we're going to talk about the Snowball Algorithm, which is the building block of Avalanche Consensus. So the Snowball Algorithm has a few parameters. N is the number of participants in the network. So I'm going to use as we go through these examples, I'll just use this room voting on what we're going to get for lunch every day, burgers or pizza for the next week as an example. So N is the number of people in this room. K is a sample size between 1 and N. So every one of us is a node, and at every time step, we'll ask K other people. We'll be connected to K other people, and we'll ask K other people what they think. And A is a quorum size between 1 and K, so that's the number of people that we ask that we need to make the same choice in order for us to say that that's the choice that the majority of the network has decided upon. And B is a decision threshold that we'll see where it comes into play later, but that's basically the number of verifications we need for a transaction before we ourselves accept it. So the intuition behind Avalanche is if we're all deciding, a group of all of us is deciding whether we want pizza or barbecue, we're going to sample K of us at each time step, and if more than the quorum size agree on a certain choice, we'll increment our decision threshold. That decision threshold starts at 0 when we see a new transaction, and we increment it up every time we ask enough people, and we see that the idea, on a more general level, the idea behind it is if the majority is voting for something and we see that the majority is voting for something, we can slowly all just start to hop on that decision, and then it'll spread throughout the network, and that's an effective way for all of us to come to the same conclusion as a majority. So every time we decide that there's a big enough quorum, we increment the counter. If the next time we don't have a quorum for that decision, or we have a quorum for a different decision, we set the counter back to 0, or we set it to 1 for the other decision. Eventually, a decision will propagate through the network as more and more nodes start hearing their friends. So it's basically like you hear all your friends want pizza. You hear them say that for 2 or 3 iterations of a time cycle, and then all of a sudden you decide, okay, I now also agree that I want pizza, and then you start propagating that out. And now slowly more and more people are propagating that, so eventually we will come to that decision. We talked earlier today when we were talking about the theory of distributed systems about liveness versus safety. And one of the really cool things about Avalanche is that liveness and safety are parameterizable. So they've set the liveness. A is a quorum size, and as A grows, there's more safety because there's more redundancy. As A grows, you need more people in the network to agree with something before you agree with it, but it's less liveness because it'll take longer to make a decision. As you require more people to decide on something before you pick it up yourself, it's going to take longer for you to pick it up yourself. But that parameterizable aspect of it is one of the main advantages of Avalanche and is why it addresses Avalanche the way I like to, or the way I've been thinking about it is Bitcoin and Ethereum were really revolutionary, and Ethereum is making a lot of moves, as we saw earlier in this section, to make these same changes. It'll become very similar to Avalanche. It'll have proof of stake. It won't have these data structures, but it'll still have proof of stake and do that energy savings. And while like Bitcoin was, I think Bitcoin has a lot of value. Obviously, there's a great community around it, but a lot of the fundamental issues with scalability and with energy consumption on Bitcoin are addressed by Avalanche. So the next thing we're going to explain is a DAG, which is a directed acyclic graph. And this is the data structure that is used in Avalanche instead of a blockchain, blocks in a linked list. And it has a direction. So you can see that if you start at the node A in this example graph on the right, and you follow the arrows, no matter what, you'll end up at one arrow. There's no cycle, so it's not going to send you to another thing. And you will end up at either the sinks D or E. But there is the idea that there's no unambiguous ordering of every node. So if we look up here at these nodes and we want to say which nodes come first, we know A comes first because it's linked to all the other ones. But if we want to ask what comes first, B or C, they're at the same level on the tree, or on the DAG, so we can't necessarily confirm. And if we want to ask what comes first, D or E, they're at different levels on the DAG, so we can't compare because they don't share a common ancestor. The goal of consensus is to prevent the inclusion of conflicting transactions into the DAG. And for Avalanche, you are able to define conflicting transactions in whatever way you want. For Bitcoin, we talked about the UTXO model a lot. So in the case of Bitcoin, a conflicting transaction is when there's two conflicting UTXOs. And new transactions are added as children to the bottom of the DAG. Here, we're going to introduce the ideas of chits and confidence. So if a node has quorum for a transaction, sorry, that should say transaction and not node, it gives it a chit. And when I say a node gets quorum, that's each time it asks everyone, and we have above, say my quorum in this room, I'm asking 7 people. I'm asking 15 people each time, and I need 10. I need 10 to say yes for me to make the decision. Every time 10 people respond to me with that decision, I'll give that transaction a chit. And nodes also have, and all the other nodes that approve that transaction will also give it a chit at that time step. And they also have the idea of a confidence, which is equal to the chit of a node plus the chit of its descendants. So as we see, W has descendant Y, V has descendant W and Y, and V has descendant X and Y, and then X has descendant Y. And it'll just add up all the chits of its descendants, because if someone is approving a transaction that is later in the DAG and the transaction earlier in the DAG links to it, it is more confirmation that that previous transaction was real and valid because we're now mining on top of it. If a conflicting transaction with Y that we just added, Q, is added, the two will be in a conflict set, and the ancestor W will retain its confidence, but all the items in the conflict set will have their chits and confidence set to 0. With conflicts, the transaction with the most confidence is in the conflict set is chosen. So if one of the transactions here, we say Y, has another transaction Z added to it that gets successes on top of it, it will get confidence and it will get consecutive successes, and then other nodes will begin to validate it instead of the other transaction that's conflicting and that's not valid. Transactions can still be added to those in a conflict set. So even if there's two transactions in the graph currently in conflict, they're not going to be removed immediately. They're going to be removed when eventually it's decided that they're in conflict. And in the meantime, new transactions can still be added if they come after the previous ones. And there's no guarantee that a valid transaction in Avalanche goes through, but that's okay, because if there's a conflict set, it's okay to not include any of the transactions that were in that conflict set, because say I'm sending something on the Bitcoin network and someone sent out a malicious attack to duplicate that transaction, it's okay if neither of them goes through because it's kind of a one-off scenario and the person can resend the transaction and know that it didn't get sent. But there is some scenarios where it does end up going through. There's a few optimizations that were added to the actual consensus implementation when Avalanche actually implemented it. So there's the idea of vertices, and vertices are what all those nodes were in the graphs that I was showing you before. When I was explaining it, we were just saying that they were transactions, but in reality, in the actual implementation, they are called vertices, and they're very similar to a block in a blockchain. They store hashes to the parents because it's not just one parent, it's multiple parents, and they also store a list of transactions in that vertices. That way, votes are for an entire group instead of for just one transaction, and the votes still travel upwards to all the previous quote-unquote blocks or vertices, but it's better to describe them as vertices. No conflicting transactions are possible within a vertice because that would make automatically that vertice invalid and never able to be accepted. And if a vertex is rejected, the rejected transaction is thrown out, and the rest are added to other vertexes to be propagated and confirmed later in the next few seconds. Finality takes seconds on Avalanche, is truly final, and is probabilistically safe, which means that this isn't an absolute guarantee, but we can set the thresholds, those variables that we saw in the first slides, to certain levels where it's the probability that a correct node accepts a transaction that another correct node rejects can be made arbitrarily low. The actual consensus implementation has a few other optimization. It asks about, when we were showing it earlier, the idea was that a vertice would ask, or that a node on the network, a validator, would ask about transactions one at a time and get responses one at a time from everyone in the class. But if I had to do that for hundreds of transactions and I had to ask 15 of you every second about what you thought about 100 transactions, it would be a lot of communication, and with blockchain, or with any computing system that we're building, we want to be as efficient as possible. So what we'll do is, if we ask you about a transaction, you'll tell us about what you think about that transaction, but you'll also tell me about the whole preferred set of transactions that you've already accepted and are waiting to have fully accepted. It doesn't do work if there's no transaction to work on. So in Bitcoin and Ethereum, blocks happen no matter what. But here, if there's no transactions being added, once transactions are confirmed, they're finally confirmed, and the new transactions don't need to, or no work will be happening until a new transaction is added. We don't need to wait for all other nodes to get back to us before a decision is made, because if we've already seen that we reached the quorum, or if we already see that too many people are voting for different things that we won't reach the quorum, then we can just go ahead and stop asking the rest of the people and save more time. In Avalanche, we will use staking to vote. So instead of doing proof of work, we'll use staking to vote on which transactions we believe in. And there's also the idea of delegation. It requires something like, I think, like 2,000 of the native token of Avalanche. I think it's like AVX or something, in order to begin staking, which is thousands and thousands of dollars. But if you have a smaller amount, like 25 tokens, you can delegate them to someone else and still earn some rewards, but that person will earn a percentage. There's also limits in Avalanche on the amount of staking power you can have. There's a maximum staking power for any individual node to prevent one person from getting too powerful. Avalanche is also, it's key to note that it's not necessarily a blockchain, but it's infrastructure for consensus mechanisms. And a new DApp can use Avalanche Consensus like a black box. It can use it like just a library. If any of you have programmed, it can just use it like a library, and without having to worry about the implementation of the consensus mechanism, it can use Avalanche Consensus for its application. This decouples the application layer and the consensus layer, and the only thing it needs to tell Avalanche is a few things about the way it defines the problem, and the main one is how it defines conflicting transactions, because in Bitcoin it's UTXOs, but in a different smart contract application, conflicting transactions will be defined differently. And that's it. Oh, any questions? Because I know we went through that a little fast, and I'm sure skipped over a little bit.
So when you showed us the DAG, you said that you couldn't know the level because there was no ancestor.
Mm.
Wasn't D and E on A and C as
Okay, so you can know the I spoke wrong. When I was saying level, you know the level, right? You know the level is in the DAG. You see that it's the same, and it has the common ancestor, and it's the same number removed. But what you don't know is within, what I meant is within the level, right? So let's go back to that slide. Okay, so we know how far, we can, well, as you say, we know the levels because we know how far it is from A. But if we look at transaction D and if we look at transaction E, we can't tell you which one came first. Does that make sense? So that's what I meant. There's not an unambiguous, there's an ordering, but not of every node. It's not unambiguous for every node. Any other questions?
While you guys are asking questions to JJ, this is the attendance code for today. If you want to go on the answers right now. Ava Labs.
Thank you guys for all sitting through this. I know it's a bit of a longer lecture, but we appreciate it.
Continue to ask questions.
Yeah, feel free to continue to ask questions, and I'd really appreciate feedback on this section. So if anyone's down to tell me if they thought it was too fast, too slow, too detailed, or if certain things need more explanation, really appreciate it. Thank you, guys.
Thank you.
Thank you, Nate. Of course. I had a question. So like, it seems like for like a lot of these like Bitcoin or sorry, blockchain protocols, they all have like their own consensus mechanism. Like, do you have a framework for determining why one would be used over the other? Is it just like what's most scalable, what has the most security? Is it like